We left off last time having taken a look at a familiar system of differential equations turned into a matrix equation. And we also know two solutions for this system. We verified these at the end of section 3.1, so we know that these really are solutions for that. And so we're going to look at each one of them in turn. And so we'll start with y1 here. And so if you notice that for any value of t that we plug in, this thing is only changing in the x direction. So the x-coordinate is changing with respect to time. The y-coordinate is not. So at any t value, this thing goes in the x direction only. Right? There's no motion in the y direction. The other thing that's worth noting is, well, the y component is always 0. So what does that mean this thing would look like? Well, if there's only motion in the x direction and the y coordinate, or the change in the y is always 0, then that means it only moves horizontally. And so since this thing is only moving in the x direction and the y is not changing, the y of t equals 0 for all t is modeling what this thing is doing, right? So since this is the case, our y1 solution produces a solution curve. And I'm going to put it in quotes because, of course, it doesn't look like a curve here. That is the x-axis on the phase plane. So what we're seeing when we look at this solution curve, to flip back to the previous page, really is this line right here. It's the only place on the phase plane where there's motion in the x direction, but there's no change of the y component coordinate. So no matter where you start on this pink line, it only moves in the x direction. And so that's what we're seeing in this particular solution right here. So the other way that this can be written is by factoring out the e to the 2t, and then you're multiplying it by the vector that says it's going to move e to the 2t in the x direction, and it'll move 0 in the y direction. Right? So let's take a look at the other one. This guy right here, the y2. Let me scoot this up so we can see it. y2 is another solution that we know is 100% accurate. And in this one, it's moving both in the x-coordinate and the y-coordinate are changing with respect to time. And so you can think of this as the x of t, and this is the y of t. And really, it's like the y of t is basically -2 times the x of t. You see it? Because if I multiply x of t times -2, I wind up with this thing. So it's like it moves this much in the x direction, and in the same amount of time, it would move -2 times that in the y direction. So apparently, both x of t and y of t are approaching 0 as t approaches infinity. And I can tell that because as t gets really, really big, both of these exponentials, because they're a negative in the exponent, are headed towards 0. This is what we would call exponential decay. So just looking at this solution curve, this is telling us that wherever you start, your x-coordinate is going to slowly decay over time, and your y-coordinate is also going to decay over time, right? And if we wanted to do this little factoring trick, we could do the same thing. The only common factor here is e to the -4t. And when we factor that out, we're left with, on the top, -1, and on the bottom, 2. So in a way, up here for the y-coordinate, it's basically saying, or for this particular solution, it's saying it follows exponential growth along the x-axis. And this one is saying it follows exponential decay along, well, it's not an axis, but basically this is the direction to the left 1, up 2. And if you think about it, left 1, up 2, that's going to produce a downward line like that. And sure enough, that is exactly what we're seeing here. This is left 1, up 2, or y equals negative 2x. Remember when we wrote that on there, I was identifying this by its direction. And that's exactly what this vector right here is doing. It's identified by its direction. So both of these things, these solutions that we proved, are solutions for the system. These are what we call straight line solutions. And they are basically the simplest solutions right next to the equilibrium point. Now remember, the equilibrium point solutions, that's just the origin. And so that's kind of a easy solution. But these are a little bit more interesting. And it turns out that if you know the straight line solutions for a system, then you know everything you need to know about that system. And so we're going to work really hard to figure out where these things are, even if not all systems have what we might call a straight line system or a straight line solution. And so just because the x-axis is a solution, notice that that doesn't mean that the solution travels at a linear or constant rate. This thing is not moving at a constant rate in the direction of the x-axis. It's exponentially growing, right? And just like this one is exponentially decaying over time. So this is where we get into that parametric nature of these equations. So time is the independent variable, and this is telling us what direction on the phase plane it's going. So you'll notice down at the bottom, I'm just going to write this in here, the e to the 2t part tells us the solution. Goes faster and faster. As t approaches infinity. So as time goes by, these solution curves, that solution curve y1 is moving faster and faster and faster. And you can see that if you take a look at the vector field for this system. If you go back and you plug this thing in and take a look at the vector field, you would see that the further you go out along the x-axis, the faster those solution curves are moving, the longer those vector arrows are. So on the next page, we're going to push on that a little bit with this idea of vector fields. And so our system, which is really this system right here, system of differential equations, can be written in matrix form, right? Can look something like this in matrix form. And the vector field for this is really just what those parameters are telling us is essentially, if you give me any x and y coordinate, I'll tell you what direction and how long that vector is pointing on the field. So for example, if we're on this page and we say, I want to know what's the vector field doing, what's the vector field value when x is 1 and y is negative 2, you'd say, okay, well, I'm going to plug that in here and say 2 times the x coordinate plus 3 times the y coordinate. That's going to be the top of this thing. So it'd be 2 times 1 plus 3 times the y coordinate, which is negative 2. And in the bottom, it's going to be 0 times the x coordinate minus 4 times the y coordinate. So 0 times the x coordinate minus 4 times the y coordinate, which is negative 2. And so all of this breaks down to the vector value of 2 minus 6 is negative 4. And on the bottom, we have positive 8. So what this is telling us is at the coordinate 1, negative 2 on the phase plane, the vector field value is pointing in a direction that's left 4, up 8, right? So you could imagine this is telling you left 4, up 8. And remember, these are the x coordinate, and that's the y coordinate on the phase plane. So over here we can do the same thing. If we want to know when the x coordinate and the y coordinate are 1/2 and negative 1, we can plug that into our system and say, okay, well, 2 times the x coordinate, so 2 times 1/2 is 1, plus 3 times the y-coordinate. So minus 3. So 1 minus 3, that gives us minus 2 on the top. And on the bottom, it's going to be 0 times the x-coordinate plus, or minus 1 times minus 4, so plus 4. So this is telling us at the point 1/2 comma negative 1, this is telling us to go left 2, up 4. Now, you'll notice that in each one of these cases, we're saying we have an x-coordinate and a y-coordinate, and then this vector field value is telling us what the arrow looks like at that point. Now, we can step down here and actually create that vector field one little vector at a time at the coordinate 1 comma negative 2. So let me find that on my phase plane here. At 1 comma negative 2, I'd have the point right here. And this thing is going to be pointing, it says, to go left 4, up 8. So I'd go left 1, 2, 3, 4, and then I would go up 8. 1, 2, 3, 4, 5, 6, 7, 8. So the end of my arrow's got to be right there. And so this takes a little bit of practice and a straight edge if you've got one. So we bring in a straight edge and say, look, I just need to make this arrow go from there all the way up to there. So at an angle, this is a little tricky to do, but let's see if I can get it. So that's what the vector field would look like at this point right here. It's pointing that direction. Now we can do the same thing for the next one, the red point that we came up with. At the point 1/2 comma negative 1, it points in the direction left 2, up 4. So I'm going to have to find 1/2 comma negative 1. Oh, look at that. It happens to be right there, right where that point is. And I have to go left 2, up 4. So left 2, so 1, 2, and then up 4. 1, 2, 3, 4. Hey, what do you know? It just so happens to be right along the same direction as that blue arrow. So try to do this without making too much of a mess. So it's pointed in that direction. Now you'll notice they're not the same length, but they're definitely pointing in the same direction. So you're probably not at all going to be surprised to find out what happens when we take a look at another one. So we're going to do this next one. We'll do this one in green and say at the x-coordinate, negative 1/4, y-coordinate 1/2, the vector field value would be negative 1/4 times 2. That gives me negative 1/2 plus 3 times 1/2. So negative 1/2 plus 3/2, that gives me 1. And in the for the other coordinate, or the other direction here, we'd say 0 times the x-coordinate minus 4 times this y-coordinate of 1/2. So minus 4 times 1/2 is minus 2. So at the x-coordinate, negative 1/4, y-coordinate 1/2, this thing is telling me to go right 1, down 2. Right? So we can plot that. My green marker is a little bit sloppier here, but it's going to get a little bit tougher to do, as you can probably imagine. At 1/4, 1/2, negative 1/2, that's going to put me basically right about there. And this is saying go, oh, whoops, I did it wrong. 1/4, 1/2 is going to be put me right there. There we go. And it's telling me to go right 1, down 2. So right 1's going to put me right about there, and then down 2 is going to put me 1, 2. So down here, and so I have to plot that. It's going to put me right about there, and you're not at all surprised, I'm sure, to find that this thing is pointed right along the same direction. Now, it's pointed along the same line, but it's pointing in this direction. Now notice, the first 2 points were on this side of the y-axis. This next point that we just did is on this side of the y-axis. And so the ones that are over here seem to be pointing up and to the left. The one that is over here seems to be pointing down and to the right. There's one more, and this is going to get a little bit hard to see, but I think you can probably predict where it's going to take us. if we have an x-coordinate of -1 and a y-coordinate of 2, that would put me right here. You can probably guess what direction it's going to point. It's going to point this way. And sure enough, when we do the math, we come up with 2 times -1, so that's -2, plus 6. So that's -2 plus 6 is 4. So that's telling me to go right 4. And then the other one's going to be -4 times this, so -8. So this is telling me to go right 4, down 8. So at this coordinate location, go that direction. So that's what we're going to do. So from here, we already made the dot, go right 4. So 1, 2, 3, 4, and then down 8. And that's going to put me quite a ways down. 1, 2, 3, 4, 5, 6, 7, 8. So if I can see it, right about there is where the tip of the arrow is going to go. And as you probably could imagine, this thing is going to wind up pointing right along the same line, but down and to the right. And so it turns out that all of these points that we've chosen are points that are right along this line y equals -2x. And if you remember, y equals -2x, that was the line that our y2 followed. So any point that's on that line seems to produce a vector that points in the direction of that line. So any point, any initial condition on the straight line solution, y2, and remember that is y equals -2x, that's the direction that it's going, has a vector pointed along that direction. And so that's true. If you go out here and you choose any value over here or up there, you'll find out that they all have vectors. They all produce vectors that are along this line. But the question is, what about something that's not? What about something that's not along that line? What if we chose something like this point right here? What if we said at the point 2, 2 on the phase plane? What is the vector field value at 2, 2? And we can figure that out. The vector field value at 2, 2 is going to be equal to, we go up here and we say, well, if we plug in 2 and 2, what do we get? 2 times 2 plus 3 times 2. So that's 4 plus 6. That's 10. Just recording my 10 down there. And then if I do 2 and 2 times this direction, you'd have 0 times 2. That's nothing. But -4 times 2 is -8. So what direction is this telling us to go? At 2, 2, the vector field points right 10, down 8. And so what would that look like? Well, I don't know. It's going to be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's going to be somewhere out here. And then down 8. 1, 2, 3, 4, 5, 6, 7, 8. It's going to be like over here, the tip of that arrow. So you can tell pretty quickly that if you drew the arrow for this guy, it still has a vector value, right? But it is not pointed along that same line. It does not belong to the family of all those coordinates that produce a vector. That produce a vector pointed along this direction. Right? So what does that tell us? Well, it tells us that even though any initial condition that's on the straight line solution produces a vector pointed along the straight line solution, we can also say any initial condition not on the straight line solution will have a vector pointed elsewhere. In other words, it's not going to point along the straight line solution. So this is a big deal. This is a really useful and interesting pattern that always works. Any straight line solution, you pick a point that's along that straight line path, and it will produce a vector pointed along either towards this way or away this way, right? Depending on the situation. Either pointed directly towards the origin or directly away from the origin. And that's just how they work. So some key observations on the next page we'll start with on the next video. So we'll end there for right now, and then we'll begin with the next page on the next video.